Okay, now this is the last discussion, chapter 12, 12.6. Okay, so we will move to chapter 13. And I hope you already have, I've uploaded the video, and I hope you watched the video that I just uploaded for 13.1 and 13.2. So I will go to 13.3. And later, after break, I think I will just go reviewing chapter 10 and 11, at least what will be on your midterm, what will be the emphasized, which part is essentials for your study, and maybe which part is, I think some parts need to be really, you need to have like more and more practice. So that will be our lecture today. Okay, so we will start by 13.3. Okay. As a conclusion from 13.1, let me just write a conclusions. At least 13.2. Okay. 13.2 is saying that so in chapter 13, we will have our typical factor function. Or we can write also in terms of the bracket like this. Okay. Now, what 13.1 says is it introduces you to a factor value function, and you can have what we call space curves. Okay. For example, when you have the helix structure, it's come from a factor function. And also, the other part that is essential in chapter 13 is on how we can relate factors with derivative and integrals. A long story short, the conclusion is very simple and very conclusive. That is, if you have a vector function and you want to find the derivative, what you're going to do is you need just to derive each component. Okay? That's how you derive in a vector function. So when you have r, the derivative will be r prime. And h prime, like that. Okay. And the same thing when you have integrations. What you're going to do is you integrate each component. Okay. For more details and for more, I think I'm not really proving like official proof, but I think you can just watch the video that I prepared. And for integrations, let me just write here. This is okay. Okay, this is just a short summary of 13.2. 13.2. So 13.1 is introductions to the vector functions, how we can make or how we can shape a space curve. We call it a space curve. Okay. So space curve means you can sketch a curve that has a sense of direction. It has a vector. And then 13.2 we deals with the introduction is actually having limit. Okay. I'm skipping limit here, but I hope you understand. If I take this derivative, which means we can also take the limit. Okay. So we take the limit, and then take the derivative, and then take the integrals. Okay. Okay. Now, what's so special in chapter 13 is actually at chapter 13.3. It is the arc length and curvature. this is what makes the chapter or the sections different from our two-dimension counterpart in Calculus 1. In Calculus 1, we also learn limit, derivative, integral, right, the very basic one. But now we are learning on the perspective of a vector. Okay, so the function is a vector functions. Okay. Okay, now to begin with the arc length and curvature, let me start with the arc length and just a review. And also, I think this is also related to your midterm, I think, right, in chapter 10. So if you have arc length in parametric, if you remember the parametric, this will be f prime t and then squared plus g prime t squared. You can write f prime g prime or df, okay, or df dt, dg dt, same thing, and then dt. Or you can have in terms of xy, like I said before, dy dx and dx dt, dy dt and dx dt. Okay, now for our vector function, suppose we have and then we are going to have t from A to B, the interval. You can write each component as x, y, and z. And we state the statement f prime, g prime, and h prime all continuous. And then we need to also mention, because it's also parametric, we can say it's parametric also, we need to mention the curve need to traverse exactly once as t increases. Okay, this is also important. It is the same as in chapter 10. It's the same as chapter 10. So in chapter 10, whenever you find any polar or maybe parametric, you need to make sure when you calculate the arc length, its movement is just once. If you, for example, the polar one, like I think I mentioned in the early class, if you take like circling around, if you take twice, then your arc length becomes twice. But in reality, it's only one time, like the circle one. Like for example, you have the circle like this. Let's say you need to compute the arc length. If you're not careful, and then maybe take wrong interval, it means that you will going to have like circling around. It's also, so imagine this is a circle. Maybe you can substitute the circle with any polar curve, like maybe the cardioid. Okay, maybe you can substitute with the cardioid like this, or any other polar curve. If you're not careful, you will get more than one, and then it's wrong conclusion. So careful on this movement. So you need to have exactly once. Okay, now then we can write the arc length in the vector functions, this will be equal. We just add all the terms. Or we can also say that this is or if you want to write more in a way more simple, this form, because FGH is component of the vector R, right? This is X, Y, Z, right? Because it's a component from the vector R. Then, if we have this F squared, G squared, and H squared, it's actually a magnitude value of the vector, right? Remember. So we can also rewrite this in a more simple way. That is, this is actually equal to the magnitude value of the R prime t. Oh, sorry, I forgot to write prime. Okay, so it should be F prime, G prime, H prime. So this is the arc length. To give you illustration, probably I can put some sketch around here. Let me take the to put on context. Okay. So here we call a space curve, and we are going to estimate or measure the length of the curve based on the interval. And actually, the same way we approach the two-dimension when you learn the last semester calculus, it's the same approach. The difference is we are just dealing with vectors. Okay? We are transformed from the two-dimension and then move to our space curve. And also, since we are dealing with parametric equations, we can also make a new parameter. We can make a new parameter. It's called parameterization. So we can take the, for example, we have t, and maybe if you change to other parameter that you can relate with t, but maybe easier to calculate, you can do so, and then you can change t. For example, we can change to u or v. It depends on the context. Maybe I will share with you just an example. Okay, if we look the example, find arc length of a circular helix. Yeah, this is a typical circular helix, cos t, and then plus sine tj plus tk. From 1, 0, 0 to 1, 0, 2 pi. Okay, so imagine how this looks like. You can take t from 0, take t from 0 to 2 pi, and then if you want to draw a graph, you can set the t for some interval from 0, maybe pi over 2, pi, 2 pi, and see how you can create a helix structure. Let me give you the So we start from t0. When t is 0, the x is 1, right? This x is 1. The sine 0 is 0, okay? And you can check with other c as well. For example, if this is 0, maybe you can check also for pi over 2, for example. Pi over 2 when y is 0, you can also check. But the question is just finding the arc length. Okay? You don't really need to draw, but actually this is if you want to draw. If you want to find the arc length, you can use the previous equations, and then just looking at these going from 0 to 2 pi. So we can take that and then write the arc length. So we differentiate. So let me write r prime t. Then we see that this is going to equal square root of 2. So this is going to be will be 2 square root of 2 pi. Okay, I think just a simple questions. A single curve C can be represented by more than one vector function.
For example, if you have and you want to rewrite the form in new parameter. If t is e with power of u, then we can write also this becoming a new parameter. And also new interval. This is we called parametrization. Parametrizations of the curve C. If you feel you need more context on chapter 13, please rewatch the video that I upload on chapter 13. Okay. Okay, still on arc length. We also have the arc length functions. I think also similar with your calculus one. So we can rewrite the arc length as a function. So it's also similar to what we have in vectors, the line segment. You can also take the arc length into functions. Okay, suppose we have vector functions. The derivative is continuous, and curve is traversed exactly once. As t increase. We define the arc length functions as t And let me just put the graph.
So what arc length function means is you can imagine the curve, and then you take the segment of that curve and take it from the initial point to some variable t, okay, as in your also similar to your line segment. Okay. So we can make this line or the curve here, the curve as a segmented curve. And we can take that as t. So the key for the arc length function is how you can parameterize, make a new parameter from the original vector function to maybe another parameter that you want to observe or analyze. Why parameterize is so essential in our analysis? Because sometimes when we are dealing with a problem, maybe related to some data you are having, if you're just looking the data, the raw data, without any modification, you'll be having difficulty on reading those charts. And if you are maybe interested on learning to become someone who are maybe working with or working as data science or data analyst, I think this is now quite popular. And maybe you've heard the big data, right? You've heard big data. But recently, the term big data, although it's already popular, most of practitioners or some experts, they say that the big data is big because it's really massive. Right? The data is so massive. But the problem is, how can take the data that is relevant? Because if we are extracting data, like when you have your account linked to many social media, many other websites, other or people or companies, they are extracting data from you, right? They also need to think which data is important. Okay? So what's the relation with this is, if we just take it all in a raw material, like really take it as it is without any further modification, further reparameterize the value, we will see that it is difficult to understand, okay? to understand directly. So if we can take the data set, like for example, if you are the, like maybe you own like company like Facebook, like, or maybe social media that's extracting data, you need data that of course you want to have like profit. So the first important thing is you need to identify how to make your algorithm, how to make people going for your website, click, and how to predict what is this person maybe what he likes, what he interested in. Okay. Like for example, like we did, or maybe you sometimes scrolling, probably scrolling social media, or maybe scrolling like an online shop. Maybe the popular one, Shopee. Oh, he said, I want to buy this. And also, the company needs to think and give you like it's actually an illusion that they give you illusions that you will going to buy the product that you don't really need, but you want to buy that. That's the dark side of what the industry is. So in actuality, to back to here, then we need to make a shortcut, or yeah, we can say we need to make shortcut which data set that we are going to extract. So the company need to extract not all data, but maybe several data that is relevant for their profit, so that they can further prolong their business. So yeah, if you want to go inside and maybe learn more about, maybe you need to learn some statistics, learn, of course, programming, but I think programming, it's already a lot of workshop or community that you can learn from. And you can start learning programming since elementary school, right? There are a lot of resources. So I also encourage you to learn, because I learned quite late, not really. Because I think before, like in the early 2000s, it's not as much as today. So today you have really a lot of resources to learn. Okay, back to here. Okay, so arc length function, and the next section will be also essentials in our subject for chapter 13. It's called the curvature. A curvature means, or maybe let me write this in a way that more easy for you. The curvature, it is related, let me write here, related to smoothness. Okay. Let me put a picture that is maybe here. We can say the curvature is how smooth your curve really is. How smooth. So what smooth means? Smooth. What's the opposite of smooth? I lost words. Smooth and the opposite word? Yes. Good. Rough. Okay. So rough, like maybe if I draw, maybe it's much more makes sense. Okay. If I draw like, okay. If I draw like this. I think it's very easy to differentiate this two. Okay? This is rough, this is smooth. Okay. Now the curvature means it's a degree of the smoothness of the curve. Okay? That's the way I think
I think for me it's easier than if you read the textbook. I think it's quite not really, because some textbook, and especially your calculus textbook, if you're reading without any basic some basic knowledge, okay, you will maybe confuse a little bit. Maybe you need to read at least 2 or 3 times, and maybe watch tutorial on YouTube, and then you more understand. And I don't really like in my lecture here. I don't blame you if you watch like tutorial on YouTube, because I think if you want to know more like in depth in your native language, I think you can just do that. Okay? My lecture is actually, I want to like give you some trigger for you that I give you some information, and you need to find the information or maybe confirm the information whether it's true or not. Okay? So university students, one thing that you need to keep in mind is when professor said something in the class, okay, and okay, the difference between high school and university. University, it is the time for you to ask the right question. But when you are still in high school, or maybe junior high school, you still can ask, but more often you are receiving information, right? You're receiving information. Oh, okay, this, and that. But university, and even if you are going to like take master, you need to do more about asking a question, not finding the answer, but rather you need to ask questions. And a good student is the one who are asking the right questions. That's, I think, relevant to your study. So back to the smoothness. So if we see from this curve, and I believe this is quite smooth, right? And what smooth means, we can also observe or analyze the tangent. Okay, thank you. Okay. So right here. But because we are dealing with vectors, the tangent, I think I mentioned in the videos that I upload, the tangent can be written as unit tangent in vector. Okay? So unit tangent. This is just a review. Unit tangent. So the derivative and divide by its magnitude. First is this. Okay. Let me mark this as number 1. Okay. So from here, you see that maybe it's changed slowly, and then maybe from here it's going to change a little bit faster. Okay. So smoothness means you analyze which section is going slower, which section is going faster. And the curvature will be averaging your smoothness, how smooth your curve really is. Okay. So we need to have one statement that clearly saying, okay, it's smooth or it's rough. Okay. Let me just write first. Okay, just write that the curvature, we are writing the curvatures like this. Curvature, this is curvature, is equal so this is unit tangent vector. And this is the parameter. Okay. and some relations, okay, that we can make to see the curvature in more general, because we are taking x as our parameter. Maybe we are taking t to make it easier to look at. So maybe if we start with dt, okay, the derivative, we can write in chain rule. Okay. So we can write the curvature as dt and remember that dx over dt is our r prime. If I take here, just to look on what this looks like here, this ds over dt. So ds over dt is r prime. So ds over dt is r prime. Right? Okay. So ds over dt, we can write this as, this is t prime and this will be r prime t. Okay. Maybe I can add some notes, okay, for the curvature. The curvature is how rapid the curve is changing with respect to the length. Okay, we will have short break and we will review chapter 11 after our break. Okay, now let's move on to the review. Okay, so let me review a little bit, okay, and which part that you need to emphasize when you study and practice or exercise. Okay, maybe start with chapter 10. Okay, chapter 10. So chapter 10, we learn first is about parametric, and second is polar. This is mainly our two distinct sections. The parametric one, I hope you still remember, okay, at least finding slope, arc length, right? Even area. I have area. Okay. And then the emphasis for the calculation will be more on polar. More on polar. It can be arc length. It can be the area. Especially finding the area and then having some polar curve. I hope still remember. Try to do some exercise on the polar curve, okay, the area. And then still in chapter 10, we have the conic section also, right? Conic sections. At least for this conic sections, this is just the basic that you need to have. Differentiate between the conics, okay? There are type of conics, right? And chapter 10 and 11, there will be more on chapter 11. So chapter 10 probably only 35%, 35 to 40%. The rest will be chapter 11. Because I think chapter 11 has a way lot of content, and chapter 10 just a limited content. Okay. So let me just focus on chapter 11. Okay, chapter 11. Chapter 11. First, we learn about sequence. Right, sequence. And then from the sequence, we know that the sequence can be converges, right? Or diverges. And how to take this converge and diverge, we are going to use the limit, right? We are to use limit. And then based on the definitions, okay, we need to have monotonic, right? Monotonic sequence, bounded, and we know that this will be converged. And then we learn on the series. But it can be 1 or 0, depends on, maybe it's easier for 1. Now the series, we also learn when the series is converged and when the series is diverged, right? And you need to distinguish, I hope you can distinguish between the series and the sequence. The sequence is just an order, okay? When the series is you are adding plus, 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 okay? But the sequence itself, we can represent the sequence inside the series, right? So we have a sequence, and we add all the sequence that becoming a series. And also you also need to remember that to make this or to prove this, we need to have the definition on partial sum. Okay? We need to have partial sum, and then we can have
limit. And through some set of methods that we discussed, like several methods we have, like from divergence test to ratio test, root test.
Then we can how to determine. So here, how to determine. Always start with divergence test. I will just take some several methods that I think quite important. The ratio test. This is geo or P series. And then the other one that is important is alternate series. And the alternate series, it can have implications on whether it's called absolute convergent, conditional convergent, or just a divergent.
I hope you still remember what this is. 3.
Okay, and then from the ratio test, if you remember the ratio test,
We can have 3 implications to make it converge, diverge, or inconclusive. Okay. Less than 1, greater than 1, I hope you remember. And then from ratio test, from those conclusions, or from the conclusion that is converged, we can rewrite the series in terms of new variable, which we include x, and we call that power series. Okay.
so from ratio test, we can develop in way more, we call this power series.
It starts from
The x to the power of n,
right.
we can have 1 plus x squared plus x cubed plus dot dot dot, and we can imagine this in terms of 1 over 1 minus x. This is the first
Representation functions.
that we learned.
The power series is 10.8, and then this is 11.8, and this is 11.9 representation function. And when we represent, we are doing it based on this 1 over 1 minus x, and then we can reform the formula and forcing it to become 1 over 1 minus x. And then still, if we look on power series, remember also, because you will have n and x, right? You have n, which is you are going to limit the n to find the convergences, but you also have x, in which the x is actually not really exactly. So for example, the converge diverge at the beginning, if it's converged, you know exactly the number. Okay, it's converged to 5, it's converged to 4, 2, 3. But in power series, the converge is getting some interval, which we call the interval of x. We call that the interval of convergence, okay? The interval of convergence. So we have the radius of convergence and interval of convergence. This is R or I. Okay. The radius means you have some set interval. You're going from some set of A to plus some value.
and minus some value. This one is called the radius. Okay, we have some certain interval. The half of it is the radius. Okay, that's the idea. Okay, so remember this. Okay, how to find the radius, how to find the interval. Okay, at least to find radius and interval, the first step you need to do in power series is always using the ratio test, because this is the implication of the ratio test actually. So if we have set of series that's having some set of x, okay, aside from n, which means that it has some set of interval that you need to figure out. You need to find which interval is converge, okay, which one is diverge. Okay, so 11.8, 11.9, and then 11.10. Okay. 11.10. 11.10 is actually an advancement or a modification of power series. Okay. So generally, you can write this. Let's say it's x minus a. Okay. Let's say you can write like this. Okay. So in 11.10, actually, this is how to expand this form, and we call it Taylor and Maclaurin. Taylor and Maclaurin. The idea of Taylor and Maclaurin is basically the same. Taylor is with A. Okay. This is at point A. Or Maclaurin is at point 0. Or at x equals 0. Is x equal A. And after several definitions, we know that the coefficient is, let me write with different color. It's related to this f with derivative n. So the function derived several times, and n factorial. Perhaps to understand more clearly on how this Taylor-Maclaurin will be written, maybe you can try. So before you start doing the exercise or practice on Taylor and Maclaurin, maybe the first thing you can do is you take some functions, maybe the easy one like sine x or cos x or maybe e to the x, and then try to develop your, maybe start this Maclaurin because it's easy, it's going to be at 0. So try to make it on your, in your paper. You try from the first derivative, second derivative, third derivative, and then you put all the functions, the result, and its coefficient inside the expansion. So try develop some essential function. Okay. Okay, perhaps let me just give you several questions. Okay? But this is more or less what I'm going to emphasize in your midterm exam. So first, you can bring your calculator. Okay, so I allow calculator to be used in the midterm. So you can prepare. If you don't have, you can maybe borrow it to your friend or maybe buy the calculator. Yeah, I think that's the important one. Okay, let's see what we have. Let me start with some set of questions. Okay, let me see. Use Maclaurin series. Or maybe find representation of series from function. Let's start with the easy one. Okay, as you can observe from these two questions, if you want to represent functions to a series, it's better to use some set of functions that are essential in the Maclaurin series. And for example, the first one is has sine, the second one having the ln 1 plus something. So you can think essential function, what they are looks like, and try to modify the series from the look of this function. Okay. So if you see here, you can relate the first one to the sine x, right? It's not too complicated. You just take the inside and then change the x. Okay. The second one, you having the ln, and of course, I think still have the essentials for the functions in the Maclaurin, which is ln 1 plus x. First changing the x with x cubed, and then after that multiply the x squared, okay, for the series. Okay. Now the problem is sometimes you are not really sure the functions, okay, or how to take the functions into its power series form and how to make it come true. Well, although it takes time, I think you can just try to confirm it like from the scratch. I think it just takes some 5 minutes to write down all the essential things. For example, sine, we can start with writing down the Maclaurin. So let me write here. It's a general Maclaurin. So we start with just a function with x 0, and then we start with the first one, and then we start with the second one, and then you can add more and more n, 3, 4, 5. Okay. Okay. So what we are looking for is we start from sine. So sine x at x equals 0. Okay. So first write down f of x, sine x, f0 is just 0. So we start looking for the functions and its coefficient. Okay. So this is also the same. We are looking for the functions and its coefficient. So the second one is the derivative. The first derivative, this is cos x, and f prime of 0 is 1. And the second derivative, you get negative sine, and it's also 0. Third derivative, it's becoming negative cos x, which is going to be negative 1. Okay. Now from this pattern, you will see that every time it's the n is from if you take this is 0, 1, 2, 3, when it's 0, 2, maybe 4, 6, and the even number, all of the coefficient will be 0. Okay? So for sine, we are just concentrating on find which one is the odd one. Okay? Now we can write down the formulations for the Maclaurin series as, so we can write down this as x. Okay, we start from x, which the coefficient is 1. Okay. The second one is 0, so we skip this, and then we have another one which is the third one, and it's negative. Okay. So we will have a negative, and then x cubed, and then 3 factorial. Let me just write 1 factorial so you will see the pattern here. And then negative 0, 1, 0, negative 0, and then you can write down the pattern. So we will have the positive 5, and then negative 7, and let me just write dot 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 like that. So we develop the sine x, okay? We develop sine x. Now we can rewrite this in terms of the series, if you would like to write. And then since we need to have its positive and its alternate signs, we can write this as -1, start from 0, and then we can write the x is an odd number, so we start from 2n plus 1 and 2n plus 1 factorial. Okay? And if you know sine, then you will get cosine easily from here, and you just derive this. So -1, -1. Okay. Okay. Now, if you know this sine, okay, so this is sine x. Then sine pi over 4x is equal, we exchange the x with pi over 4x. So let me write, this is pi over 4 x, and then 2n plus 1, and then 2n plus 1 factorial. Now it's up to you if you want to make it more convincing, like maybe 4 going down here, and the up, the top equation just pi x and then 2n plus 1. That's up to you. But I think if you just write this, because you have limited time on your exam, I think it's just okay. For me, it's okay. Unless maybe if they have options, then you need to pick options that is equivalent with the answer. Okay, now the next question is the second one here. The f of x is x squared ln 1 plus x cubed. Now first we can start from the ln 1 plus x. Okay. Now if you don't know how, you can start practicing the how to develop the Maxwell rate from scratch. But it takes time, 5 to 7 minutes at least. But if you write maybe faster, maybe you can write it really fast. But if you know and some of the essential functions, you can just write down what it is. Okay, so you can write down this is equal to and I start substituting some relevant variable. And then if we have x squared, then we will have x squared like this. or maybe just directly write +2 on the x like this. Okay. Okay. Okay, let me go through next question. Still related to the ln and Maclaurin. So if I have f of x, ln, and 1 plus x, and 1 minus x, okay. I think I mentioned this in your test, right? In your test, the online test. So the first 3 non-zero terms of Maclaurin of f of x are okay. Now, if we want to solve this, if we look back to what we have in ln 1 plus x, this is what we have. Okay. We can rewrite this, or maybe let me copy this.
because it's asking 3 non-zero terms of Maclaurin, and we know that we need to check the all the n actually. So probably it's better if we are taking from n equals 0.
So let's rewrite this in terms of from n equals 0. So we just added okay, and the ln, if we have because ln, we can rewrite this as minus, right? And basically, if we have minus, let's just take the
n equals 0 and exchange the x.
Exchange the x. And simply it's become n plus 1 and then negative 1. Because we have negative from the x and coming outside. So f of x is ln 1 plus x minus ln 1 minus x.
Since it's negative, it's become plus.
Right, it's become plus. So we will have
and then you can check from 0, 1, 2. So check 0, it's become 2. 0, 0, it's become x. So 2x.
So this will be 2x. Okay. Check for n equal 1. For n, let me write here. For n equal 1, 3, 5, 7, it's becoming 0, right? So we are just skip 1, so take 3. We take 2, sorry, we take 2. It's become x cubed. Will be 2 over 3 x cubed. And then similarly, we will have x5. So this will be the three non-zero terms. Let's actually still have n equal 3. Well, no need to write all, just 3 non-zero, I think it's okay. Okay, maybe last question. Last question. Interval of convergence for the series. And this morning I upload another video for practicing, so I will also attach to the Moodle later. It's still practice. So I hope within this additional videos and our practice today, it can help you guide which one or which one that is more emphasized or maybe more will be more having more discussion in our midterm. And to help you out with some technical calculations, please prepare calculators. Solve this as usual. The power series need to reflect on ratio test to check on how good the convergence is. How about the radius? What about the interval you will get from the ratio test? Okay. The ratio test start by taking the ratio on an plus 1 and an. And this we can write first. We let an is equal to x with power of n and n. Okay. So take the absolute value to remove our alternate signs. So we can have an plus 1. And also, whenever you find any series that has a power like this, it's an obvious to use the ratio test. So obviously, ratio test will be your priority. Whenever you find, for example, 1 like n squared n, blah 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 with some complexity here, the best way to take this, any guess? Any guess if you have a 1 over n squared of n plus maybe sine n, any complexity here? What method you're suggesting? The most logical method, easiest to use. Yes, comparison. So you can have either direct comparison or limit comparison test. I think you're good to go. I think to be safe, just use limit comparison. I think for most cases, if something like this happens, then you can compare it to some theories that is easy to determine, and then you can compare between those two. Okay. Or if not, okay, if not comparison, not you check divergence, not easy, You can check geometric P series, or if not, the one way to solve probably using the telescoping sum. Especially if this series having some, maybe having the form like this, you can make it something minus something. It's probably a hint to use telescoping sum. Telescoping sum. Okay. Okay, now let me just finish this, and this will be having x, having 3. So you will have, and you need to have less 1 to be converged, right? To be converges. So it should be, okay, x should be on this, but need to check, okay? Check. Okay.
So this is our interval probably here, but we need to make sure whether we need to include both or maybe we need to remove some of them. Okay, so we need to check -3, put on the series, and you need to determine the series, whether it's converged or diverged. Okay, I hope you can practice. And also I will make some, probably some short notes for guiding you for midterm exam. Okay. I think that is for today. So we will see you at the midterm next Tuesday. So maybe you can also remind your friend if they forget to come.